Good morning, all of you. Today, my topic is nitro compounds. Introduction. Nitro compounds are an important class of organic compound which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atoms by nitro group. Nitroarenes group is directly attached to benzene ring, can be prepared rather easily, and have been used as synthetic reagents since long. But nowadays, even nitroalkanes are being prepared and used on a large scale. Structure of nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen. But actually, nitro group is established by resonance and is hybrid of two equivalent contributing structures. The resonance hybrid structure is confirmed by the fact that the bond length of each nitrogen-oxygen bond is 121 picometer or 1.21 angstrom, which is intermediate between nitrogen and oxygen single bond length and nitrogen double bond oxygen double bond length. In case of nitroarenes, resonance of the nitro group with the ring can also takes place, giving rise to the additional contributing structures for the molecule. Nomenclature of nitro compounds. Nitro compounds are named by writing the word nitro before the name of the parent compound. The number of nitro groups and their position are also suitably indicated. Example: nitromethane, nitroethene, etc. Classification of nitroalkanes. Nitroalkanes are termed as primary, secondary, or tertiary according as to the nitro group is attached to a primary, secondary, or tertiary carbon atom. For example, primary nitroalkane, secondary nitroalkane, and tertiary nitroalkane. Preparation of nitro compounds. Preparation of nitroalkenes are usually prepared by the following method. First, vapor phase nitration of alkanes. This reaction involves the substitution of a hydrogen atom of the alkane by a nitro group. It is carried out in the vapor state by heating the alkane with nitric acid at about 700 Kelvin temperature. Limitations of this process. During nitration of higher alkanes, all possible isomeric nitro compounds are formed. Moreover, rupture of carbon-carbon bonds also takes place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane results in the formation of a mixture of 4 nitro compounds. Due to the formation of complex mixture of products, this method is not used for the laboratory preparation of nitroalkanes. However, the method is widely used for the commercial preparation of nitroalkanes. Mechanism. The reaction is believed to involve the formation of free radicals, but the mechanism is not well established. Second, action of silver nitrate on alkyl halide. This is the method generally employed for the laboratory preparation of nitroalkanes. When heated with silver nitrate, alkyl halides undergo nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitrites. This is because NO2 is an ambident nucleophile. However, the mixture of alkyl nitrites and nitroalkanes can be separated by fractional distillation, oxidation of amines. When an amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Preparation of nitroarenes. Nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agents generally used are concentrated or fumic nitric acid, mixture of concentrated or fumic nitric acid and concentrated sulfuric acids. This mixture is the most commonly used as nitrating agents. Mixture of concentrated nitric acid and acetic anhydride or boron trifluoride acetyl nitrate obtained by mixing nitrogen pentoxide and acetic anhydride. Fifth, nitrogen peroxide in the presence of anhydrous aluminum chloride. Choice of nitrating agent. The choice of nitrating agent to be used for the nitration of a given compound depends upon the following two factors. First, nature of compound to be nitrated. Second, nature of nitro groups to be introduced. In the nitration of aromatic compounds containing electron releasing or activating groups such as NH2OH and CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In some cases, even dilute HNO3 can be used. For nitrating compounds containing electron attaching or deactivating groups such as COOH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. Nitrobenzene and meta-dinitrobenzene, for instance, can be obtained from benzene under the conditions shown below. Mechanism of nitration. Nitration of aromatic compounds like the other aromatic substitution reaction is electrophilic in nature and involves a nitronium ion NO2 positive as the attacking electrophile. The mechanism may be summed up as follows by considering the nitration of benzene with nitric acid and sulfuric acid mixture. First step is generation of electrophile. Second step is formation of carbocation ion, and third step is proton transfer from the carbocation to yield the final product. Evidence in favor of the above mechanism. It has been shown above that aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as electrophilic reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is a slow rate determining step involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involves the elimination of protons from the intermediate ion by the heterolytic cleavage of CH bond. A carbon deuterium bond is broken more slowly than a carbon protium bond. The absence of isotope effect in aromatic nitration can be justified only if the rate determining step of the reaction does not involve any cleavage of carbon-hydrogen bond. This means the final step involving the abstraction of proton through the cleavage of carbon-hydrogen bond can't be rate determining step. Therefore, the step leading in the formation of carbocation must be rate determining step, as it does not involve any cleavage of carbon-hydrogen bond. Once formed, the carbocation loses the proton relatively fast to form the final product. The absence of isotope effect also rules out the possibility of a single-step mechanism for nitration. This is because single-step substitution can't take place without cleavage of carbon-hydrogen bond. As such, it must exhibit isotope effect, but this is not in actual practice. Hence, aromatic nitration in a stepwise process in which the formation of carbocation is the rate determining step. Comparison of nitration of arenes and nitration of alkenes. It may be noted that nitration of arenes takes place at relatively low temperature, whereas nitration of alkenes require at very high temperature. This may be due to fact that the nitration of arene involves the initial formation of electrophilic reagent, while the nitration of alkanes is supposed to involve the initial formation of free radical. The formation of free radical takes place homolysis and requires stronger condition than the formation of electrophile, which takes place through heterolysis. As such, nitration of arenes takes place more easily than the nitration of alkanes. Nitroarenes can't be prepared by action of silver nitrate or aryl halides because of very low reactivity of aryl halides towards nucleophilic reagents. Physical property of nitro compounds. Physical state. Nitroalkanes are colorless, oily liquids when pure. They have pleasant smell and are sparingly soluble in water, with the exception of a few compounds including nitrobenzene, which are yellow oily liquids. All other aromatic nitro compounds are yellow crystalline solids. Nitrobenzene has the odor of bitter almonds and is known as oil of myrrhine. Second, solubility and density. All the nitro compounds are heavier than water. Nitroalkanes are sparingly soluble in water, while aromatic nitro compounds are insoluble in water. They are, however, readily soluble in organic solvents such as alcohol and ether. Stability. When heated strongly, polynitro compounds decompose with explosive boiling points due to presence of highly polar nitro group in their molecule. Nitro compounds have strongly dipole-dipole interaction. Consequently, they possess high boiling points much higher than hydrocarbons of comparable molecular mass. However, most of the nitro compounds are volatile in steam. The melting and boiling point of nitro compounds gradually increase with the number of nitropropyl chemical reactions of nitroalkanes. First, acidic nature tautomerism. Nitroalkanes containing alpha hydrogen atom exhibit acidic behavior and form salt in the presence of strong alkalis. The acidity can be attributed to the fact that first, nitro group has a strong electron withdrawing inductive effect. Second, the anion formed after the removal of proton from nitroalkane get resonance stabilized due to ability of nitro group to accommodate negative charges. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperature, the oily drops of nitroalkane do not separate immediately, but we get another form of nitroalkane known as the acid nitro form, which slowly changes into the nitro form. This is due to the fact of primary and secondary nitroalkanes exhibit tautomerism, the tautomeric forms being nitro form and acid nitro form. The tautomeric equilibrium between the two forms lies almost completely towards the nitro form because it is stabilized by resonance of nitro group. Acid nitro form is relatively stronger than nitro group. An important feature of acid nitro form is that it can act both as electrophile and nucleophile. Unlike primary and secondary nitroalkanes, tertiary nitroalkanes do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Reduction of nitroalkanes. Reduction of nitro compounds is one of their most important reactions. The reduction of nitro group takes place in stages. Nitro compound to nitroso compound to substituted hydroxylamine and to primary amine. The product actually obtained depends upon the nature of reducing agent and pH of the reaction medium. Reduction in acidic medium. When reduced in acidic solution, nitroalkanes form primary amines. Second, catalytic reduction with LiAlH4 or H2 in presence of nickel, palladium or platinum catalyst also yields the same product, and that is primary amine. Third, reduction in neutral medium. If the reduction is carried out in neutral solution, a hydroxylamine derivative is obtained. Third, hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkanes undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. Secondary nitroalkanes are hydrolyzed to ketones and nitrous oxide by boiling with concentrated HCl. Tertiary nitroalkanes are not hydrolyzed by acid. For NF reaction, when sodium salt of primary and secondary nitroalkanes are hydrolyzed by boiling with dilute sulfuric acid, aldehyde and ketones respectively are obtained. The reaction proceeds through the acid nitro form of nitroalkanes. Fifth, action with nitrous acid. Primary, secondary, and tertiary nitroalkanes exhibit different behavior towards nitrous acid. Primary nitroalkanes react with nitrous acid to form nitrolic acid, which dissolve in NaH and produce a red solution. Secondary nitroalkanes react with nitrous acid to form pseudonitrols, which have blue color but do not dissolve in NaOH. Third, tertiary nitroalkanes and nitrorene do not react with nitrous acid since they do not contain any alpha hydrogen. Sixth, halogenation. When treated with halogens in slightly alkaline solution, primary and secondary nitroalkanes undergo halogenation at alpha position. Nitromethane on chlorination in alkaline medium gives trichloronitromethane, also known as chloropyrene. Tertiary nitroalkanes do not undergo halogenation because they do not have alpha hydrogen. Seventh, condensation with aldehydes. Due to presence of active alpha hydrogen atoms in them, primary and secondary nitroalkanes undergo aldol type condensation with aldehyde in the presence of base to form nitroalcohols. Manich reaction. This is a condensation reaction which involves formaldehyde, ammonia, or a primary or secondary amine, and a compound having at least one active hydrogen atom, such as primary or secondary nitroalkanes. Chemical reactions of nitroarenes. Nitroarenes are chemically rather inert compounds. The nitro group is firmly attached to the nucleus and can't be replaced by other atoms or groups under ordinary conditions. Some important reactions are: first, acidic nature. Unlike primary and secondary nitroalkanes, nitroarenes do not have any alpha hydrogen atom. As such, they do not exhibit acidic character or tautomerism. However, nitro group compounds having Two or more nitro groups attached to the benzene ring and somewhat acidic in nature due to the strong electron withdrawing group effect of nitro groups on benzene ring. Second reduction, the most significant reaction of nitro compound is the reduction under different conditions to give different product. As already stated, the reaction takes place in stages and the nature of the final product depends mainly on the pH of the reaction mixture. Reduction in acidic medium. On reduction of acidic medium with active metal and acid such as zinc and HCl or tin and HCl, nitrobenzene yields aniline. Mechanism. The mechanism proposed for the reaction involves a number of steps in which addition of electron and proton takes place. Nitrobenzene free radical anion and nitrosobenzene free radical anion and are formed as intermediate. Catalytic reduction. Reduction of nitrobenzene with H2 in presence of nickel and palladium gives the formation of aniline. Reduction in neutral medium gives the yield of hydroxylamine stage. Reduction in alkaline medium. Nitrobenzene yields different products depending upon the nature of reducing agent employed. Example, when nitrobenzene react with Na3ASO3 and NaOH gives azoxybenzene, and nitrobenzene with ZnNaOH in CH3OH gives azobenzene, and nitrobenzene with ZnNaOH gives hydrozobenzene. Azoxybenzene is formed by condensation of nitrobenzene and phenyl hydroxylamine. There is sufficient evidence to show azobenzene is formed through the intermediate formation of azoxybenzene and further reduction. Hydrozobenzene is similarly formed by the further reduction of azobenzene. Reduction with LiAlH4 gives the yields of azobenzene, and electrolytic reduction gives the yield of para-aminophenol. Selective reduction. In case of compound containing more than nitro group, it is possible to carry out the selective reduction of one of the group employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. This reduction is known as Ginin reduction. Electrophilic substitution. Nitro group being an electron withdrawing group has a strongly deactivating effect of electrophilic substitution reaction of benzene nucleus. However, under strong condition, nitro groups compounds may undergo electrophilic substitution in meta position with respect to the nitro group. It may be noted that nitrobenzene does not undergo Friedel-Crafts reaction. For nucleophilic substitution, the nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature, but this very electron withdrawing influence of the nitro group makes the benzene nucleus liable to be attacked by nucleophilic reagents. Thus, unlike benzene, nitrobenzene on heating with sodium hydroxide gives small amounts of ortho and para nitrophenols. Mechanism is shown to the formation of para nitrophenol. Fifth, replacement of the nitro group. In case of polynitro compounds, one of the nitro group itself can be replaced by nucleophilic group. Example, para-dinitrobenzene gives para-nitroaniline in the presence of 2NH3, and in the presence of KOH gives para-nitrophenol, and in the presence of C2H5ONA gives para-nitrophenyltol.